Hi guys, welcome to Learning Electronics Repair. This is the ATX power supply we were playing around with a couple of videos ago, where I was trying to work out whether a subscriber suggestion that we could connect the 5 volts and 12 volts output in series would give us 17 volts. The subscriber said that should work, and I thought, well, actually, if we get the grounding right and isolated between the two 12 and the 5, then yes, it should work. So I tried it, and if you watched that video, which I will link in the description to this one in case you didn't, you will know that it was not successful. And the reason it was not successful was because the way these windings are connected on the transformer. So basically the 12 volts is not a separate winding from the 5 volts, it is a tap. Or shall we say the 5 volts is a tap on the 12 volt winding. So they're both on the same winding and they both have a common ground, and you can't isolate the two, or at least not easily, okay? You may think it's impossible. If you watched that last video, I figured it was possible to effectively disconnect one of the tapped 12 volt windings from the other and connect it to a different ground, but then effectively I only have half wave rectification. So at that point I thought it wasn't worth going any further with it. But what I would like to try, and I've been thinking this for some time, is can we get 24 volts out of the ATX power supply? Can we get a 24 volt supply at high ampage out of an ATX power supply? Well, I think we can, but then again, I thought we could do the other thing and we couldn't. So, being a bit of a glutton for punishment, let's have a go and see if I can do it. First of all, I'll explain on paper what I'm going to try and do. Then we'll have a look to see whether that appears to be feasible, and if it does, we will try it. Okay? So first, the explanation. Here's how this is connected up. We have the primary of the switch mode transformer, and one end of it connects to 2 transistors, and most ATXs are actually bipolar transistors, not MOSFETs, and they're both NPN. So we have one here and the other one connected here, and this goes to hot ground, the negative end of the large capacitor, and this end has 320 volts, which is the rectified and smoothed mains. It could be more. If this has active PFC, it might be 380 volts, but we'll put 320. The voltage isn't that important, the principle's what matters. So these 2 transistors are switched by the controller. And the controller switches the transistors on and off in turn, so they never switched on at the same time. First this one is switched on and then switched off again, then this one is switched on and switched off again, and back to this one, on and off again, and it does this at a high frequency. What that effectively does is it alternately connects this end of the primary to 320 volts, and then to 0, and then to 320, and then to 0, and so on. That effectively puts a square wave on this end of the coil, and the square wave is between 0 volts and 320 volts. The other end of the transformer primary doesn't connect to ground. It connects to another inductor and then through a capacitor, high voltage capacitor, and this connects to the 2 large smoothing capacitors or bulk capacitors, which are connected between the 320 and hot ground. So your 2 capacitors are here in series like so, positive, negative, and this is 320 volts, and this is hot ground, 0 volts. There's also connected across these 2 capacitors, 2 resistors, like so, and they connect to there. And these are high value resistors, 270k, 470k somewhere in that region. And what these two resistors are actually for is to make sure that the voltage is balanced equally between these two capacitors, because different capacitors have slightly different capacitance, slightly different leakage current. So that's what these resistors do. They just maintain the voltage there. And the voltage is half of the main supply voltage, 160 volts. This circuit, by the way, is called L for inductor, L, L, C for capacitor. And what this does basically is convert this square wave that's driving the transformer into something that's much more like a sine wave. Okay, that's what the LC does, because transformers want AC, sine waves, to drive them efficiently. Now the transformer has secondaries, and these drive the output voltage, but on ours you don't have a separate secondary for the 5 volt and 12 volt. The 5 volt is a tap off the 12 volt winding. So what we have is, we have a winding connected here to safety ground. Okay, this is a secondary. I've drawn it over here so I have a little bit of space to draw this diagram properly. Okay, and on here is a tap, a connection, and this goes to a diode. And then from the other end of the winding, we have another diode, like so. This is your 5 volts tap, and this is your 12 volts. And then we have the same thing again. There's 2 of these secondaries. I'll draw this one upside down because it makes the diagram easier to draw. So with this one, we have ground. Top of our coil, we have the same thing, a coil with a tap on. Okay, this is 12 volts, and this is the 5 volts, and we have 2 more diodes. Okay, these diodes are actually in one package, or rather the 12 volt diode is one double diode and the 5 volt is another double diode. So they look like this basically, with 3 legs, and internally they have 2 diodes connected like this. This is called common cathode because the cathodes are connected together, and the cathodes is the center pin. Okay, so you'll find a symbol like this usually on the package. Sometimes it will say plus AC, AC. They're marked in different ways, but it's the same thing. So we have 2 of these. So these 2 diodes are actually in one 3-pin package, like so. And these 2 are also in another 3-pin package. I'll just draw it like this so we can connect this one here down to there. Okay. And then we have the smoothing inductors and capacitors. You'll have a, I'll just join that to show it's joined. Okay, you'll have an inductor, electrolytic capacitor connecting to ground, and that is your 12 volts out. And you may well have another capacitor here as well. It just depends on the design of the circuit. You may or may not have another one there. And we'll have the same on this. So we'll have an inductor. We'll have a capacitor on the output to ground. This is 5 volt out. And we'll have another capacitor possibly here. And the 2 double diode packages. And we'll put 5 on that 5 volt. Now there's 2 things you might wonder. First of all, where's the 3.3 come from? On the power supply I looked at, it actually comes from the same winding as the 5 volt does, but it had an inductor before the double diode, which reduces the voltage basically from 5 to 3.3. On another power supply it might be different, but on the one I have, that's how it is. The other thing that's important to mention is these two coils are in anti-phase. That's normally drawn by putting a dot at the end of the winding. And in this case, we'll have a dot here and we'll have a dot here. The 2 points with the dots are in phase. So it means that when the sine wave here is reaching the positive phase, that one is doing the same thing, okay? And then the negative, the same. So if these two ends are in phase, this one and this one must be in anti-phase. So when the sine wave here is going positive, on here it's going negative. And when this is going negative, this is going positive. What that means is that these two diodes fire not in tandem together, but alternate. So first this one conducts on the positive half cycle. When this goes negative, this one goes positive and that one conducts. And then when this goes negative, this goes positive, this one conducts again. So the conducting, as that is switching the wave, 320, 320, these are firing in the same way, yeah? Alternately, they're not together. So that's what we have. So if we connect our scope to here and to here, what we should see is something approximating a sine wave, and there will be an anti-phase. So we should see that when this end is going positive, this end is going negative, and vice versa. So let's get the scope and let's have a look. Here is the power supply, and I've attached two scope probes to it. As you can see, I have a dual channel scope, so we're going to monitor the waveforms. I've tagged wires on just to make it easier. This is a ground wire, so I have one of my scope probes clipped to ground. Remember, only ever clip one scope probe to ground unless you know they're both connected to the same place, and then you can connect them both, but it's not good practice because one day you will forget when you're not supposed to connect them both. So guys, always just connect one ground point to your scope and you can't go wrong, okay? The reason for that, by the way, is if you connect both ground points to different places on the device you're working on, you are shorting those two places on the circuit together. And almost certainly you did not want to do that, okay? Let's have a look where these wires are going. Well, you can see this is the diode that is feeding the 12 volt supply. This is the 5 volt supply, this is the 3.3 volt supply, and these are these double diode packages. So the middle pin is the two cathodes connected together. That one, this one. The reason for these holes here, by the way, this PCB will take two different size diodes. Mine's the one with the legs further apart. That's the only reason we have those two holes. And the two wires I've soldered on are to the anodes of the two diodes that feed the 12 volts. And these are connected to different secondaries. So basically this is ground, okay? So we have the tap feeding into the 5 volts here, and it's also feeds the 3.3. And we have the other tap on the same winding there, which is a 12 volt tap to the diode, okay? And on the other coil, effectively again, this is ground, this is the 5 volt output, and the 12 volt comes at this pin, the opposite end of the transformer, to here. So what I'm expecting to find is that these 2 points are driving a sine-ish wave in anti-phase, yeah, as I described on paper. So let's have a look to see if that's what's actually happening. I have my scope set up. I have both trace 1 and trace 2 set to 10 volts per division. They're both set to DC, so we have DC coupling and we have DC coupling times 10 probes. So if the waveform actually is AC, it will effectively go positive and negative at this point. If it's offset, the line will move as well, okay, or the middle point of the waveform will move. Like all of these rather crazy experiments I try on here, this is the first time I've tried it, so I honestly don't know what's going to happen. But I'm hoping to see two anti-phase waveforms, as I said, so without any more talking rubbish and stuff, yeah, any more crazy talk, let's try it. Well, there it is. So they are kind of sine-ish. Let me turn the sensitivity down a little bit. Yeah, that's that one. And that's that one. So they're definitely in antiphase and they're definitely sine waves. So the question I thought is, well, if first one diode is effectively rectifying that off for the positive, then this one, then back to this one, and back to this one, what's happening to all the negative half cycles? Because they're being ignored, they're not being used, yeah? The diode, the double diode, only conducts the positive half of that waveform. But the negative half of that waveform should give us minus 12 volts, don't you think? So, look what I'm going to do. We've seen on the scope then, this works as I described it would work. And we can also see that the negative half cycles on both windings are effectively going to waste. This coil only feeds the diode when this end is positive, and this one only does the same when this end is positive. When this end is negative or this end is negative, it's not conducting. So what we can do, at least the theory goes, is this. We can connect from here to here, and we can connect another double diode, but this one in the reverse direction. Okay, that way. Again, this is a 3-pin package, and this is common anode. So the symbol on this one, if we look at it, will be different, and we will have the two diodes shown like this on the symbol. Common cathode, common anode. Okay, you can get common anode double diodes. They're not so common as the common cathode, yeah, but you can get them, especially made for negative supplies. If we add that diode, we can then put a inductor in here. We can put a capacitor here, and this will be the opposite way round. Negative to the voltage rail. This will be ground. Again, we may put another one in here. We'll make it the same as that side is. We'll probably find as well, actually, there is a fairly low value resistor here to put some load on the supply. And if there is, that's just to help the regulation of the voltage. We can do the same with ours. We can put a resistor in here. Same value to ground in the same thing. And this should give us minus 12 volts. But that is the theory. And there's only one way to find out, yeah? So, first of all, I'll see if I have one of these common anode diodes. If I don't, there's no reason why I can't use two diodes. You can get diodes with a metal tab and two legs. Just a diode in a single package. And I can use two of those, literally. I can just use two of these side by side, okay? And just wire them so these two pins are connecting together, and as long as I do it in the right polarity, we have our common anode diode. Okay, so that's the other way if I don't have one of these. Another thing, how much current can we draw from this? Well, so the theory goes, if this, for example, was 12 volts at 20 amps, which is not unreasonable for an ATX power supply, then I should be able to draw half of that power from the positive supply and half from the negative supply and still have the same load on the circuit that's driving it. So if I connect between plus 12 volts out and minus 12 volts out and get 24 volts, I should be able to get 10 amps from that. Okay, double the voltage, half the current, because wattage, power, is voltage times amps. So on this case, watts, it's 12 times 20 is 240 watts. And in this case, 24 times 10 is, surprise, surprise, 240 watts. So our power supply would be working equally hard in either configuration. And I think that is totally sensible, yeah. I mean, let me know in the comments below. But in the meantime, let's just go try it. Well guys, as you can see, I actually do have one, which is this one here. So with this one, if we put the positive, the red lead to the middle pin, this should conduct. Yeah, on the other side, it won't conduct in the opposite polarity. Okay, and then the other one obviously is the other way around. So this one with the red lead to the outside pins conducts. Okay, so we have exactly what we need. We can check the specification of this, but I'm confident this will handle more than the voltage and current we want. We'll have a quick look, and if it's okay, then we'll attach this to our board with a capacitor from the common anode, and let's see if we get 24 volts. Here is the data sheet, and this says switch mode ultra fast power rectifier designed for use in negative switching power supplies. That's just what we wanted. Common anode, dual rectifier, 8 amp per leg, 16 amp in total. Nice. And this is rated, I believe, at 200 volts. So that's just fine. Let's solder this on with a capacitor and let's see what we get. This is the 12 volt double diode for the plus 12 volt supply. So I'm going to just fasten my diode with the two outer legs directly across these. It doesn't matter which way round it goes because they're both just anodes. So it can actually go on either way round, this way or this way, it wouldn't matter. Okay, but I'll probably just tag it on over here like so, whichever's the easiest to do. Okay, so we can get that, yeah, in here, that's fine. Just attach one leg, attach the other leg. Okay, so that's soldered on, and then the middle pin will be the negative output. I'll just add a little bit more solder to this one, I think. Yeah, that looks like it's a better connection. Yeah, okay. And what I need to do now then is to take a capacitor with the negative end here, the positive end to ground, and that's our minus 12 output. Let's see what capacitors are on this board already. Well, that's the capacitor on the 12 volts. What is it? Where is the value? Must be on here somewhere there. 2216. Now this will be connected through one of the windings on this inductor. So we probably need more smoothing than that, especially at high currents, and we need an inductor like this off a scrap one. Okay, possibly one of these capacitors the other side of the inductor, but just for experimentation I'm going to attach a 2200 directly from the output of this to ground. So we use the capacitor 2200. Here's ground, just tag that onto there. Okay, and this is our minus 12 volt out. So if we now measure from here, this is the plus 12, to here, we should have 24 volts. Let's see if this works. Okay, I've attached the ground lead of the meter to ground, so I should now read plus 12 and minus 12. Okay, let's power this up and see what it does. Okay, we're on. So this should be minus 12. Actually about minus 14. And this is plus 12, about plus. So I'm actually getting a higher voltage on here. Minus 13.6. That's be almost certainly because I don't have the inductor and the other capacitor in. So it's not smoothing the waveform as well. Between the two then, I should be able to read 24. Okay, so from here, to here, which is the 12 volts. What have we got? About 25, 26 volts. Okay. So I'm getting a bit close to the rating of this capacitor. I need to have a quick look to see how the inductor's wired on this one and salvage a few more parts, and I think we will have 24 volts. But basically, the answer to the question, can we get 24 volts out of an ATX power supply, is yes. Let's look at the way this is wired up then. So we have here the center pin of the diode, which goes to here. This is actually one pin on this large inductor that comes out on the other side, which is here. We can see that with a multimeter. So we go from the diode to here, comes back out here. And this only goes to one place. If you look, there's just one other thing attached there. Okay, and that is actually a wire link. We can see it there next to the inductor, and that comes towards this capacitor, which is here. This is the positive end of the capacitor. This is the 12 volts out. And there's possibly a resistor connecting to ground to put a bit of load on this. So let's have a look. So we go from 12 volts to ground. And we read about 220 ohms, okay? So if we take an inductor off a scrap power supply, we find a 220 ohm resistor, we can make our circuit the same as the one on the plus 12, and then hopefully we'll get a pretty much stable 12 from both, giving us 24. I have an inductor off a scrap power supply. This is pretty much like the one that we have on this board. It looks like that these two windings, the red ones, were connected in parallel. They were connected to the same place. And I'm fairly sure that is the 12 volt inductor because it's the same on our board. So I'm going to put this inductor in series with the capacitor and the diode. Okay. And then I'm going to connect a 220 ohm resistor across the capacitor as a load. And we should have basically the same circuitry we have on the plus 12 volt supply. So let's get that sorted. And there it is. So you can see these two wires are going to the inductor here. Okay. That's connecting to the output of the diode and to the negative end of the capacitor. Positive end of the capacitor to ground over here. And these are not touching each other, by the way. They're a long way apart when you look from this angle. Okay. And the resistor is connected across the capacitor to ground to give it the 200 ohm load, the same as the other one has. So hopefully now that should give us actually plus and minus 12. Let's try it. Okay, so we'll connect to the plus 12. I have the black meter lead connected to ground. So here is plus 12. Let's switch on and let's see what we get. Almost 12. What about the minus? It's still reading minus 14.5, so I'm actually getting a bit more than 12 minus on that rail, and I'm not totally sure why, but is that a problem? I mean, I'm getting effectively, if we measure across the whole thing, 26 volts. So from plus 12 to minus 12, 26 volts output. I can only guess that the difference on the minus is because it's slightly asymmetrical, the waveform maybe that's driving the transformer, but it looks symmetrical. I don't think I've missed anything else in the circuit, so they should effectively both be working the same, but that's what we have. So as a final check, let's just connect a bit more load to this. We'll put a couple of light bulbs in series, 212 volts giving 24 volts. These are 22 watt each, so 44 watt basically, which at 24 volts is a bit less than 2 amps. Let's try it. We're ready to try it then, guys, with some load on. So I've connected the light bulbs between the minus 12 and the plus 12. I've also connected the ground of my meter to minus 12, so hopefully these will light up and I can measure here and I will have plus 24. Maybe more stable or more accurately than before. I was thinking now, because Detlef is hiding around the corner, that maybe I'll get him to switch this on and I'll go hide behind the cupboard, because if he's going to go bang, this is the point he's going to go bang. No, Det has ducked behind the cupboard again. He's not too sure about this.
Let me get my helmet.
No chance. Let's switch on. Well, it's working and we have 24 volts. I won't leave it on too long because it's going to get very hot and burn the desk, and this diode needs to be mounted onto the heatsink. But guys, it works. So with the addition of one double diode, a capacitor and an inductor, both of these of which you could rob off a scrap power supply. The double diode, you'll probably have to get one from somewhere because it's reverse effectively direction than normal. It's common anode, but you see it works. So you can get 10 of them from AliExpress, probably for $1, maybe less. And we have a nice 24 volt power supply out of an ATX power supply, one ATX power supply, not two in series. I just need to make a proper job of this with the heatsink on this really, but I'm sure I can manage that even if I do something basic, such as just effectively bolting the diode onto the side of the heatsink somewhere up here and just using the fan, which is part of the ATX power supply, to keep it cool. So after the debacle of the 17 volts from an ATX power supply, I think now I've got one a bit better and got 24 volts from an ATX power supply. Hope you guys enjoyed that. I hope you learned something. Nice to see for once the theory actually works. So I look forward to hearing from you guys down there, comments below, and I also look forward to seeing you all soon on another Learn Electronics Repair video. Ciao for now, guys.